So today we will carry on talking a little bit about this linkage between mechanisms that we've been attempting to do. And I've laid out a couple of different paths. Since we had so much time last time doing the COMSOL stuff, I have kind of a backup, which I'd prefer not to use, but I will use if necessary. But the main theme from last time was that we're looking at pore mechanics, being the word really to represent HM coupling, hydraulic mechanical coupling. And we approached it in a couple of different ways. We approached it through deriving the finite element equations based on flow and on mechanical behavior, and then trying to figure out exactly what the couplings should be between those. And although we didn't go through it, we also referenced the idea of Poroelasticity, 1941 BO paper, which derives it based on continuum mechanics principles. So whichever comes easier to you, perhaps, is the one that you should maybe go after. And so what I thought today, since all of the modeling that anyone ever does revolves around this adage of GIGO, garbage in, garbage out. If you don't have a code that's doing what you already think it's doing, then you might as well give up, because the results obviously will never be of any utility to you. And so I thought that since there'll be many systems that you'd be dealing with where you might want to figure out whether what you're doing makes sense or not, is that perhaps the first thing that we'll talk about is the issue of validation and verification. And so many people use this word interchangeably. I think they're subtly different. I tend to use them interchangeably, and I can certainly never remember which term, validation, verification, means what. So I grabbed the definitions for these. So verification, the process of evaluating a system or component to determine whether products of a given development phase satisfy the conditions imposed at the start of that phase. So I have to decipher that myself, but what that says to me is that you're figuring out whether the physics and chemistry and properties, behaviors that you put into a system actually work out. So of course, if you're missing a physical behavior that's not represented in your model, then you can still verify that your solution is correct, but you'll never reach the true solution because you won't have that physics. The subtle difference between validation is against the physical system. So you're modeling against some observations. If your model doesn't include the components of the observations, the physics of the observations, then you won't get the right result either. So one is checking your model against rigorous solutions for the physics of that model, PDEs and solution of PDEs, which is really all we can do in this class. But also, the other thing you might want to do is make sure that your model represents not only the physics that you include, but also reality. If you're missing an important piece of physics, which is key to the observation, the outcomes you get, then your model isn't going to be successful, even if it's verified against the proper PDEs. So subtle difference, but and certification. Certification is when you give some warranty to what you're doing. So that's something that we should apply to all of the things we do. Otherwise, you don't do it, and you should do it early on as well, right, in a variety of phases. The other point we've tried to make in this class is you don't start with the most complex model you could ever imagine and then work from that. Typically, when you build a model, you build it incrementally. You make the most simple case that you can accommodate. You try it out. If it works for that, great. Then you go on to the next step. Clearly, if it doesn't work for the simplest case, it's not going to work for the most complicated case. And so I think that's just the standard way of doing anything that any of us do in life. And so I just moved it must be a bad connection in this. Yeah. And so regardless on the way that we derive this, whether we derive these equations from the finite element statements and then look at how the couplings occur, or if you look at BO Poroelasticity, which is really what this is, then you can use those approaches to be able to come up with some examination of what are the conditions that should be represented by this model. And so what I think it's worthwhile doing today is we'll talk about implementation of this, hopefully in COMSOL. So for those of you who are still coming in, We like to use COMSOL. It's not been very easy for us with the connection, but so that's what we'd like to do. So we can certainly talk about how we implement it. It's very simple, actually quite straightforward, but also think about what the outcomes would be for the physical models that we'd expect and how we might define what those outcomes are. So let's step back a little bit in terms of Poroelasticity and refresh our memories of exactly what we do. This is, if you like, the very basic summary of what's going on. We talked about it last time, but let's reiterate it in broad terms. We satisfy an equilibrium equation. It's F equals ma. So it's actually this right-hand term is this, basically. This is the inertial term, this is the body force, and all these others are essentially body forces as well, depending on the sign convention. And so this conservation equation satisfies those. We have definitions of strains, both in normal mode and in shear mode, as displacement gradients. And we have an additional strain which represents the volume strain of the fluid. So the change in volume of the fluid over the total volume is the definition of this fluid strain. We have constitutive relationships. We have the ones that we talked about in terms of Hooke's law, written in terms of the usual forward way, strains being related to stresses, but also fluid pressures added in it. Fluid pressures, through the effective stress law, don't act on the shear behavior. And we also have the inverse of those relationships, which are just these. These are simple to invert because it's just 1 over, but this is a bit more complicated. And in this particular case, the stress-strain equations are written in terms of volume strain components and normal strains. So they're just chosen to be written that way for some way. And so in addition to the constitutive relationships, we also have a constitutive relationship that accommodates fluid behavior. So volume strains in the fluid are a function of stresses we might apply to the system, and also fluid pressures through some coefficient. And we can get the inverse of those. And so these constitutive equations, either the forward or the reverse, however you want to label them, are the ones that define our behavior. I suppose actually it's this one here. If we write these constitutive equations in terms of volume strains, I guess this is just modifying this one, we can write them in terms of strains, and fluid pressures that result. So once we have those constitutive relationships, we can put them into the equilibrium equation. Once we have the equilibrium equation, we modify a few things, and we come out with an equilibrium, basically a Navier equation, which is just a fancy way of saying the equilibrium equation with constitutive equations embedded in it. And it now includes the dependent variables that we have for our system, which are displacements, x, y, and z, and fluid pressures. And so we'll have kind of 4 degrees of freedom in a 3-dimensional system. So that's the solid part. The complicating factor a little bit for the way that the BO derivation goes through is that it defines behavior in terms of these not so obvious coefficients, H and R, Poisson ratio and modulus we certainly know, shear modulus and Poisson ratio we certainly know, but also in terms of the values of these other coefficients. And so in terms of the definition of those coefficients, and they come only from the solid part, if you like, the equilibrium part of the equations, they define behavior in terms of this coefficient H and this coefficient R, and also a coefficient Q, which goes into the flow equations as well, which I don't think comes up here. So certainly modulus and Poisson ratio we kind of know how to get. If we know modulus and Poisson ratio, intrinsically we know shear modulus, which is equal to modulus over, what is it, 2 times 1 plus Poisson ratio? I think so. Or is it 2? Can't remember offhand. And in addition to those, we want to get magnitudes of these other coefficients, h and r. And so the way to get those is that, and also alpha, I guess, right, which is not included here, this alpha value here. And so those come from being able to figure out what h is from observations, which allow us to calculate this. And if we know what both h and alpha are, and we can also measure the value of r in some way, which we'll talk about in a second, then we have a way of getting this factor q. So the equilibrium equation with constitutive behavior in it is the first one. And the other relationship we have is continuity. Continuity of volume or continuity of mass. It's written in terms of volume in this particular case because these are velocities rather than products of velocities and densities. And so if we throw Darcy's law into this, this is just the change in volume strain with unit time of the system. And so it's the amount of fluid source volume that goes into or out of the system by both fluid pressure effects and by strain effects. And so if we throw this definition of this expression into here, then the overall left-hand side here, which is the right-hand side here, is just due to those two components, right? Rate of change of pressure with time, rate of change of strain with volume strain with time, which go into that. And so when we implement it in COMSOL, rather than the way that we derived it before, it's easy for us to see that portions of this will be covered by different parts of the operation. So this first part here is the solid mechanics part, which is taken care of just by applying forces as boundary conditions and displacements as boundary conditions and solving the system. And an additional body force gets added into this to take care of the magnitude of the role of fluid pressure in deforming the system. So this is a pressure gradient multiplied by a coefficient. This coefficient is between 1 and 0. As we'll see, and it acts on this. So this is the extra term that we'll want to add. Likewise, in our flow equation, if we deal with the flow equation in COMSOL on its own, the part that will get taken care of is with this. And actually, you remember last time when we tried to do this, the actual equation we were solving was just the diffusion equation in terms of concentrations is equal to 1 over q times change in concentration with time, plus an extra term, which is going to be this. So the part that gets taken care of in COMSOL in a regular basis is this, and the only part that we have to add, I guess, is this part on the right-hand side. And they're actually very similar to each other, as you pointed out. One is a gradient in space, one is a gradient in time. But in the finite element equations that we deal with, they get modified in a certain way. So that this is we write this in terms of a pressure change in time, and so it's not by accident that they both operate on this variable alpha. And when we actually solve this expression, it's actually the time rates of changes of these properties that we use. And so this ratio dp dx is actually this. And this, of course, here would be, since volume strains epsilon v are equal to strain in the x direction plus strain in the y direction, which is equal to change in displacement in the x direction with x plus change in displacement in the y direction with respect to y, then the time rate of change of this, strain rate, will be just this whole thing multiplied. Oh, let me not do that. So therefore, for instance, epsilon dot x is equal to the rate of change in time of the displacement in the x direction with respect to x. And so this term here is actually quite similar to this. Pressure, displacement, dt, dx. In terms here. So the symmetry that you see in these equations is actually the same symmetry that we kind of alluded to last time. I think it's kind of a ways back here. But the fact, this part here, is that in these coupling relationships, they happen to be the transpose of each other. And so the symmetry between the displacement equation on the top and the fluid pressure equation, continuity equation for fluid transport on the bottom, is kind of embodied in this linkage term, which is this. So this is alpha d dp dx. This is kind of alpha times d epsilon dot d. I guess it's not epsilon dot, is it? It's epsilon. D epsilon, change in strain, volume strain as a function of time. So these are those two terms. And this term is this other term, which in the BO equation is just 1 over Q, whatever that means, multiplied by a pressure change. And so the meaning of these cross couplings in this continuity equation are the two effective compressibilities we have. One, when we apply a displacement and we squeeze an amount of fluid out of the system by compressing it, fluid goes out. And one where we change the pressure, and by compressing the fluid, we need to put some more fluid into the system to be able to make up for the headspace that we make. And so that's the intrinsic connection between those. So, but if we want to implement this in COMSOL, which is what we're going to attempt to do now, is we need to be able to figure out just these two last terms that deal with this. If we want to be able to figure out exactly how our behaviors, our system's behaving, then exactly in the same way when we talked about constitutive equations for solid mechanics, we talked in terms of two-dimensional problems, plane strain, plane stress, one-dimensional problem, full lateral restraint, zero lateral restraint, and we could rearrange the equations so that if we put a load on a column, we could calculate what the displacement would be by figuring out what the strains are. So you can do exactly the same kind of step in a more complicated system like this, where we have fluids involved, but to figure out what the base case behaviors might be. And so to do that, it's worthwhile backing off a little bit and talking about what the behaviors are that we expect to get out of it, and what these physical coefficients mean. We can define the behavior for the system in terms of these four coefficients, as it turns out. So these are the ones that are embodied in the different components of these constitutive equations. So what we can do is you can use you don't have to look at spatial variation in behavior. You can apply some loads or stresses to a system. If those stresses are uniform, then it really is characterizing the behavior at the constitutive level. And so you can use the constitutive equations directly to figure out what the displacements and fluid pressures would be. And so let's try and understand the system in that mode. So these are the four basic parameters that we need to be able to define the system. Modulus and Poisson ratio together are embodied in the shear modulus, so those reduce to 1. And these coefficients H and R, which are actually measurable properties, are typically translated into these other components of Q and alpha. Sounds complicated, but let's go for at least a physical understanding of what's going on. Simple case. Take a sample, take a piece of rock, take it dry, no fluids in it, or air, I guess is the fluid, and you apply some stresses to it. If you apply a stress to it, these are written this way because in Bio's paper, the other complicating factor is he uses the mechanics sign convention. Tension is positive, but let's not worry about that. So let's think about it in this term. So you apply a stress to this in this direction, then we know from if there's no change in stresses in the horizontal direction, if we set these equal to 0 and don't allow them to change, then the strain that we get in the x direction is given by the stress divided by modulus. So this is just Hooke's law written in its simplest way. And we know that as we apply this, the strain in the horizontal direction will be equal to Poisson's ratio multiplied by the strain in the x direction. So these are just the straightforward, simple manifestation of Hooke's law where there's no fluid pressure changes present to mess things up. So that's the simplest way that we can look at it. So that's one thing that we can solve for. So we know, for instance, that if you load something, it develops fluid pressures initially when you load it. When those fluid pressures are dissipated, the behavior of that system should be exactly the same as if it doesn't have fluid in it at all, right? Because the pressures have changed initially, but they've gone back to their original condition, and therefore there should be no influence of that. So using these, this understanding is important to be able to understand, the long-term compression behavior. So that's useful. What happens if we take the sample and fill it up with water? And so obviously when we take this sample in air and compress it, what's different is that the air is compressible and it flows very quickly out of the pores, and so there's no pore pressure change, and so we don't have to worry about it. If we have a fluid in it, and if we jacket it so the fluid can't get out, all of a sudden that fluid is quite incompressible. In volume sense, it probably is incompressible. If you look at the compressibility of water, it's something like, the stiffness of water is 2 GPa, that order. Stiffness of rock or concrete is probably 40, 50 GPa. And so you always think of water as really a compressible fluid maybe, but it's not. Volume-wise, if you compress it with an all-around stress, it's close to being very incompressible. And so that's the essence of pore mechanics. So what we're going to do is we're going to take a sample and we're going to cover it in latex, so it's in a jacket, completely sealed. We're going to have a tube that accesses it, and we're going to know what the volume of that sample is, the total volume. We're going to make sure this is a really thin capillary, so it has no real volume that we have to worry about, or I guess we could cut it here and measure behavior right at the outlet. And then what we could do is we could suck on this. So it's a straw that we suck on. If we are able to suck on it and some fluid comes out, we can use the constitutive behavior to be able to figure out exactly what the response is. So we're going to apply some negative pressure to it, and as a result of that negative pressure, there's some volume of fluid that comes out of the system instantly. So we're not worried about the transients. So we apply this and we get a volume. This is our definition of volume strain of the fluid. This is fluid strain, fluid volume strain, which is just the change in volume of the fluid divided by the total volume of the sample, which is this, including the solid and the fluid. And our constitutive relationship from Biot's equations is this. The strain is due to changes in total stresses that are applied on the system, plus changes in fluid pressures and these coefficients. So what happens when we suck on this? Well, we have a sample. The external stresses are atmospheric. When we suck on it from the inside, the external stresses don't change. There's still atmospheric pressure acting on the outside. And so the changes in these, as we talked about when we talked about the other constitutive matrices, this is the change in stress and the change in strain that results from that change in stress. So likewise, the change in stresses are 0. All of them are 0. And so if we measure this change in volume, and we know what the volume of the sample is, then we have this term here. And if we measure the pressure we have to apply to do this, then we know what this coefficient R is. So we can calculate what R is as a function of just that simple experiment. So the other thing we can also do is measure not just the volume of the fluid that comes out of the system. What is the volume change of the sample? The volume change of the sample will respond to the fluid that's coming out. And I suppose if the grains of the sample, the skeletal compressibility was 0, then it would be exactly equal to the amount of fluid that came out. But let's not make that assumption. So now let's write the constitutive relationship for the volume strain of the sample, which includes a collection of grains and a collection of fluid inside those grains. And the constitutive relationship for that, if you just go back up to here, you can see it here. So this is the one that we've just used here. No, which one? This is what we just used here, right? This constitutive relationship. And which is the one that we are going to use now, I think is this one, which is just the inverse of this relationship. I think that's what it is. Yeah, so this is this. So if we look at the volume strain in the system, we end up with that volume strain, which we're not going to set equal to 0, but this is something we can measure. So this would be equal to the change in volume over the total volume. This was the change in fluid volume, but this is the, if you like, the total volume. So this is the change that you measure if you're measuring the external change in size of the sample. So call it T. And since the stresses that we've applied on the outside of this haven't changed, then all the stress changes have to be 0. And therefore, if we measure the same pressure change that we got before, and we measure this volume strain, we're able to calculate this other parameter. So we can calculate how we've been doing this. I guess we've been doing it the opposite way. We measure a pressure change by sucking on the sample. We measure the volume change of the sample, not of the fluid, but of the sample, and we end up being able to get this magnitude. So we have this coefficient R, we have this coefficient H, which are what are used by BO. And so now we can get this just from doing the dry experiment. We can get both of these from doing the wet experiment. This one by measuring the volume strain in the fluid. This by measuring the volume strain in the sample overall. And we can use those in some useful way. Modulus and Poisson ratio give us shear modulus. This BO coefficient is given by knowing Poisson ratio and shear modulus and H, which we've just evaluated. And if we now know both R and H, and now alpha, then we have this value 1 over Q. So it becomes an alphabet soup, and that's not what's important. But having some physical feel for these behaviors are. And the most important part, do it dry, get the elastic moduli, which are drained behavior. Right? By definition, we're not developing fluid pressures, so they're drained, would be the terminology that's used. And then do it wet, sealed inside a sleeve, and measure two things, the change in fluid volume and the change in overall volume. And the difference in those says something about the physical system, and as we'll go back. So what do these? So the other way to think about this is, actually a useful way to think about this is that we can think of this behavior as being, what is this? This is equal to, which one's which? This term here, well, what would we surmise if we look at these equations? It's kind of a bit of a mess, right? But if you look at this expression here, this term here is saying something about the change in volume of this system as a function of changing the fluid pressure. And it only results from the change in fluid pressure. So you can think of this as really being something that acts on the compressibility of the fluid to be able to give a volume change in the system due to the fluid pressure change. And so physically, if you think about what we're doing, is that these things together, this gives us the delta V of the fluid alone. This must give us, one of these gives us the complete behavior of the system, and the other one, I think, yeah, so I'm guessing that this gives us delta V in the skeleton, and then by definition this gives delta V together in the skeleton and the fluid. So that's really all we're subtracting from each other in a physical sense. And so our utility in using this now is to be able to figure out exactly how we could, if we go ahead and mess around with COMSOL, how we figure out exactly what the magnitudes of the displacements or strains or fluid pressures might be that we get in the system. And so here is a simple way to be able to do that. Let's take a column. You can think of a column also as being of some height but of infinite magnitude. I think if we said before, we can make life easy for ourselves by having Poisson ratio of 0. The reason that you use cork in bottles has a Poisson ratio of 0. Push the cork in the bottle, it doesn't snap the neck off. It doesn't expand laterally. And so if we use Poisson ratio of 0, it doesn't matter if we're plane strain or plane stress, the deformation that we get by applying some load is just going to be this magnitude here, because the other strains horizontally are not constrained. There is no strain horizontally, right? Strain in the horizontal directions, if this is 0, have to be 0, and therefore there's no constraint on this being pressed down. And so that we make life easy for ourselves by doing that. We can choose a Young's modulus, a stupid one in this case, 1 Pascal. It's not going to be that small, but it doesn't really matter as long as our units are consistent. If we choose a permeability magnitude of some small amount as well, then we can define that. And so what are we? Yeah, so this is our permeability. If we choose a value of the alpha coefficient, so remember total stresses are equal to effective stresses minus alpha times pore pressures. So we just made this equal to 1, so that makes our life easy. And if we choose unilaterally this compressibility of the fluid coefficient to be very small, then we'll end up not having to worry about that term. So we can choose a value of 1 over q. So we're choosing a value of 1 over q based on some assumptions here. So what do we expect to get for our behavior that we can check up on? Well, let's use the constitutive relationships that we have to be able to figure out what our initial fluid pressure. So what we'd like to know. What is the fluid pressure at T equals 0 plus? Would be 1. So in other words, what we're going to do is we're going to add a load on here, which is a stress in the vertical direction for our system. It's going to be equal to -1, I guess, in BO terminology, but let's not worry about that. And so how do we be able to solve for this system of expressions? So we could, for instance, take this constitutive law and we could rearrange it in terms of volume strain. And if we do that, we end up with this expression here. We only have one component of volume strain because there's no lateral strain in the directions because Poisson ratio is equal to 0. And if we rearrange for that, then this is just my scribbling out. It's a function of the fluid pressure, the value of BO coefficient, and Q. And so if we can calculate what this volume strain is, we have a chance of being able to figure out what this fluid pressure is. If we write the constitutive relationship down here in terms of the vertical strain and the horizontal strains and the vertical strains together, so this will not be 0. This is not 0 necessarily. And so we can rearrange this expression in terms of this just by accommodating these two terms together. And we get now a stress, an equation that includes both the stress that we're going to apply to the system, the fluid pressure that we'd like to figure out, and the magnitude of the strain that might go into it. We know the magnitude of the strain from this, so we can substitute in here. And if we do that, we end up with being able to calculate the magnitude of the fluid pressure that's generated as a function of the stress that we apply to the system as a function of material properties. Shear modulus, Poisson ratio, the alpha and Q values, which we both have, and the alpha value. Turns out that all of these components in the first term are basically zero, and so when we load it, we expect that it represents this case of a very soft medium where all the fluid can't escape from the pore structure quickly, and therefore the initial condition is that the fluid pressure in the medium is exactly the same as the stress that's applied above it. So physically what that means is you load it, the fluid pressure in this block immediately jumps to the same stress, which means that if you look at effective stresses, which are total stress which we're applying is equal to effective stress minus alpha times P. So if we apply 1 unit here, and this basically increases by 1 unit, I guess they're the negative of each other just by the terminology, then the change in effective stress that occurs has to be 0 to make that true. And so if the change in effective stress is 0, and it's effective stress that causes deformation, then the deformation also has to be 0 initially as well. And so the physical reality of it is that the fluid pressure being applied, I guess, if you use this sign convention appropriate in here, the fluid pressure that applies stops the deformation from occurring. So that's one thing that we could check, is that when we apply a load to the system, that in this particular case for these particular variables, and we could change the variables, that the pressure that gets induced by applying this load is equal to the load that's applied. So that's one thing that we can do. The other thing that we could do is that when this load gets applied, so in other words, if we think about this block, then initially when we apply this load, the pressure, well, let's ignore that the fluid has any self-weight. So maybe the initial pressure has no self-weight, is just 0. We apply a stress of sigma z, and the pressure goes up to that magnitude. But typically on the top boundary, one common condition to apply is to have 0 flux going out of the bottom, and to have this pressure here being set to the atmospheric boundary condition, the original boundary condition, which requires that it modifies. So although at time t equals 0 plus, it will look like this, it's still equal to 0 at this point. And so the distribution of pressures will actually look like this. So this is initially T1, T2, T3, and this will be T infinity at the bottom. And so what we can do is we could also use that to be able to calculate the time taken to be able to, for it to go to half consolidation. And that's probably more than I really want to explain here. But you can solve the PDE that represents this case. And if you do that, you find out that the displacement at this surface, if you go to your consolidation solutions, UZ in this particular case, looks something like this. It scales with, goes from 0, which we said at time 0, and what will the magnitude be at time infinity? So we can, if we know that modulus is equal to this. So if we know that strain in the x direction is equal to the change in stress, actually in z, right, divided by modulus. And if we know that the stress we apply is 1 and the modulus we apply is 1, then the strain is equal to 1 as well. And so what we'd end up calculating would be that this ultimate magnitude of this deformation would be exactly the same as the height of this, right? The strain, if a strain is equal to 1, it's equal to the change in displacement over the length. Not sure if we've classified this length here, is equal to h. And so this value here, I guess, would be equal to h. Ridiculous, of course. It doesn't turn itself inside out, but that's just because we've chosen some crazy numbers. The crazy numbers actually don't stop it from executing. And this time, instead of using time, we can scale it with a dimensionless time, which is a function of, just by rearranging this expression, is some coefficient multiplied by t times a dimension squared. And the characteristic dimension of this is just the height of the thing. And so what we'd find out is that this goes down to some value and asymptotes. And all this is saying here is that if you look at the solutions for this PD equation, for this to get to h over 2, then the magnitude of this non-dimensional variable to get there is something like 0. It's actually 0.198, I believe it is. Interesting, the things you remember. But it's this number. The time to 50% consolidation, for those of you who are geotech type peoples, is 0.2. And so long as you can define this variable in terms of the appropriate units for this particular expression, this diffusion equation, which is shown here, and essentially, if you like, the magnitude of this C coefficient is about equal to the permeability divided by the dynamic viscosity and multiplied by the bulk stiffness of the fluid or the solid. So those are the right units to be able to do this. So it doesn't matter for us. All that matters is that we can figure out exactly what that time might be as a function of the coefficients we use. And so hopefully you followed that. Hopefully it wasn't too convoluted. But the basic principle is that you want to be able to apply some very simple conditions that you think are realistically enough to exercise different parts of the model. Exercising the magnitude of the fluid pressure you might generate, which is kind of the essence of poroelasticity, and exercising the time it might take to dissipate those fluid pressures, which is the second part of what we talked about. And I suppose ultimately that the final deformations of this thing are given by this final magnitude here. So yeah, so we know three things about this system. We know that the initial pore pressure should be equal to the stress that we apply to it. That's one, for the conditions that we choose. We know that the time it takes to get to 50% displacement is going to be given by this number here. And we know that the final deformation, when everything's said and done, should be equal to the height of our system. So those are three things that we could run a model against to be able to figure out whether it would work. So let's not look at these expressions anymore. Let's try and see if we can get this to work. So you better hope it works, otherwise it'll do some more derivations. Okay, let's see how we're doing here. Oh, good. Oh, God. So just have to try another port, I guess. See if we can do that. No, it's just a... No, it's actually doing it. It's just a little script that we've added, that my computer consultant for me has added. So I think anyway, SSH. I'm just trying to find a port that works. Is anyone watching which port it logs on to? Does it log on to the same port each time? Let me do this. That may not do it. Perhaps isn't a good omen in that. Thank you. It worked in my this script worked in my office before. So it's hammer 11. Did anyone notice what the other numbers were?
So you can use mine.
I think it's the same problem. I think it just
Like already getting.
you're logged in. What port are you in?
I use another way. Just use the way you used before. Use the remote connection.
Oh yeah. This is no different. This is just going in the same way. What it does is it dynamically allocates the memory to different nodes, and so when you try and run it, if there isn't enough memory there, it fails. So, what node number are you? What node number? Does it say hammer something when you log in? Look at your prompt. It says hammer, then a number at the end of hammer.
Yeah, hammer.
So it keeps on logging. 11 didn't work before, so yeah. So SSH. But when you look, okay, let me do that again. So. Hammer 20. So are you using up all the bandwidth in here? So it's logged me in a different location. So let's see if this will work for us now. Okay. So we're in. I happen to have a. See if it'll work better than last time. Okay. Well, that's kind of curious because it ran just fine before. Always a lottery. Always a lottery. Well, let's build it from. Yeah, geez. Yeah, well, it's interesting. Didn't have that problem before. See if it. Okay. All right, well, let's build it from scratch. What would we want to do? So clearly I can't quite run it. That seems very, very strange, seeing as how it ran 2 hours ago from a different wireless network. What do we want to figure out? So we know that to represent this behavior, I guess let's go back to here. We might not be able to get to full validation of it, but we know that on the solid mechanics part, we have to add something that says something like minus times a coefficient times change in pressure with space, dp dx. We know that we're going to take the time derivatives of this, so this becomes a time derivative as well. So I suppose this would be something like minus times coefficient times d dt dp dx. Okay. So we can think of this as basically a body force in the x direction. And of course, we have three equations. We have two-dimensional problem. We have equilibrium equations in the x and the y direction, and a flow equation. And so we'll have one of these in the x direction and one in the y direction with a similar value. So that's one thing that we'd want to do. And so we'd have the equivalent of these two things, where the only thing that would change would be that this would now be dy. Okay? And so the other thing that we'd have is an expression like this. And this other expression would be something like alpha times change in displacement in the x direction with respect to x plus change in displacement in the y direction with respect to y. Right? This is epsilon v. And we want it to be a change with respect to, I'll write the ddt afterwards, but of course the ddt has to operate on this thing here. But it's a change with respect to time. And so we know that for each of these expressions, we're going to have a source term which adds to this behavior, and we're going to have a body force which adds to the equilibrium of the system. So that's what we're going to attempt to do. So let's see if it's going to be fast enough for us to do that. Didn't like us, so we'll go back here. We'll go back to these components: structural mechanics, plane strain, static analysis. Let's add it. I'm not going to do flow analysis. I'm going to do, we tried doing this last time, didn't we? So I'm going to use diffusion equation, and I'm going to use this transient behavior. I'm going to make myself a little geometry. Let's make it start off from 0, 0 to 1, 1. It's very, very, oh no, that's faster than it was last time. There's still a bit of a lag between the clicks, which I can hear, maybe you can't hear them, and it doing stuff. Yeah, so are you still on? I'm not sure whether it affects or not. All right, so yeah, it's very, very slow. So comes up with diffusion first. So what are we going to want to do? Let's go back to this. We said that we want to have some component in here which represents this behavior. So something that says this expression. So I guess I should, maybe I'll just write it up here so it's up here. So alpha times rate of change with respect to time of displacements in the x direction plus displacements y direction. This is, by definition, the only components of volume strength, because epsilon z into the page is equal to 0. So what does COMSOL do? Well, what it is going to do, we're going to want to figure out exactly what the coefficients which are defined in these expressions. Which it's not going to unlock for us. Maybe it is. So we are in the flow part. So a change in concentration with time. So this is what we want our coefficient to be, I suppose. This is going to be the magnitude that we put in. We know that from looking at this that the concentration is going to be since I can't write it on the screen at the same time, something like this. Alpha to epsilon. So this is our expression. We're going to use the diffusion equation, which is delta CS dc dt. We have del dot minus d del c. This is this term. This is going to be this. This is going to be this. And equals R is going to be this, which is going to be this. And so what we need to be able to do is to be able to figure out exactly how to put that in. And so the easiest way to do this, you remember that our value for this was 1, you might not, e minus 3 in our validation part. I think the value of dTs was 10 to the minus 5, right? These aren't the most crucial parts, but that's fine. And the value of this. So what's the value of this going to be? Well, what we need to figure out are what the other terms are. And so I guess we can't find them out here. Let's see if we can open this up at the same time. Equation system. So, equation system. So this looks at, well, this particular one for concentration. So if you look at the variables, what it will do is kind of define some of these variables. You could probably guess what some of them are. And I'm not sure it says it explicitly in any particular place. I think what we're going to find out is that concentrations, which are our pressures, so in other words, things like dc dx, I think is going to be in COMSOL's parlance cx, dc dy, in COMSOL's parlance is just cy. Concentration is equal to c, I'm guessing. And I think these terms, I'm guessing, is that ux in this is going to be in COMSOL would be u. Displacement in the y direction. In COMSOL's parlance, I think it's v. And therefore dux dx is equal to ux. And duy dy, I think it's v1, lowercase v. And let's see if we can find, yeah, here we go. So this is the diffusive flux. Diffusive flux is the diffusion coefficient times, which is this term here, diffusion coefficient in the xx direction multiplied by dc dx. Diffusion component in the xy direction times dc dy. And so I think that's true, what we've had up there. What about the displacement components? So this is, I guess this is perhaps only including the parts. No, it seems to have Tresca stuff in here as well. So, okay. So what's this? There, here we go, right at the top. Strain, shear strain in the xy direction is dux dy plus duy dx, right? This is shear strain, half, engineering shear strain. Normal strain is dux dx. And so what that's telling us is that if we want to put something in for this term here, then what's it going to look like? It's going to look like something like minus alpha times let's see if I can remember the derivative with respect to time of ux plus the derivative with respect to time of v1. So this term here, it knows what the displacement gradients are. You want to know how these change over one time step because you're using the time derivatives of these. Maybe you could add them both together, but I think this is perhaps a better way to work. And so we want to add something like this. And so what we could do, what we would want to do, would be to, with this newfound knowledge, we'd want to go back here and let's do this. It's actually running quite quickly now. Okay, got it? Alpha BO. And then this would be so no, that's not right, is it? I think it needs so yeah, I can't remember offhand without. It's a shame the other one didn't count. Multiplied by, and it would be the derivative. I think that's the right term. I think it's square brackets plus the derivative, and then we just put these other terms in here. It's displacement gradient in the x direction with respect to t, and oops, doesn't like that. And displacement gradient in the y direction with respect to t. It's not the right expression exactly, but something like that. It doesn't like it, so not quite. Anyway, so but that's what we would do if we could bring it up with the appropriate module. Hopefully it'll save it, even though it's incorrect. Does anyone know whether the brackets should be rounded, or maybe it doesn't? Just like, you think they should all be square or rounded? Inclined to think they should be rounded. I guess we could look back in the other. Oh, maybe. Might actually work, who knows? Frightening stuff. All right, and so you'd save that. And the complementary part is the plane strain part. And we would want to go in and do exactly the same things. So this is the behavior we've got. Modulus, we said, was 1. Poisson ratio, we said, was 0. Density, I think it's probably not a problem if it's weightless. It might not like it, but it's probably okay. And constraints. So this is the body force. It doesn't actually give the it doesn't give the equations here. And so the body force would be, if we go back to this, how are we doing for time? Doing okay. So this is the body force that we apply to each of these expressions. Body force is something like alpha BO times the change in pressure with x. And so the body force Fx would be something like minus alpha times change with time of pressure in the x direction. And likewise, in the y, change with time for pressure in the y direction. We've said that this actual term is what? You with me? And this would be it. So they would look something like, individually, minus, I'll type it up so you see exactly what it is. What's it going to be? It's going to be something like, I don't know if plus or minus, I can't really remember, but that's not hardly the point, right? Okay. Minus alpha BO, whoops, times, yeah, diff, yeah. I think. Oops. Doesn't like it. Okay. Sorry? What won't be? Say again, Sharon?
You put that won't be consistent with the constant gain. The same thing also happens to the R term. Because it gives you that the red in the unit, that makes the unit is not consistent.
Yeah, but that's maybe because we haven't told it what the BO coefficient is. I mean, we can make sure internally that our units are the same. I mean, most fine element, COMSOL is a little different in that it's set up to have actual units that you apply to this thing, but most, when it used to be that many, so long as you use consistent units, you're okay. You can check whether the units are consistent. And I guess we could check whether the units are consistent in this particular case as well, right? So let me just finish off this. Diff CY, right? And so, yeah, it's not going to like that one either, or yeah, it doesn't like it either. Yeah. So yeah, we can check for consistency of these units in the systems that we're solving. So we want to make sure that the units of force are in newtons per meters cubed. So we can do that, right? So we could check whether that's correct. I guess we probably won't get time to actually run this, but. What are those? So we think that Fx is equal to plus or minus, don't know if it's plus or minus, alpha okay, so actually, all right, that's right. So is it smart enough to realize whether that's the case? So what you say, Chang, is right. dt dp dx. We can look at the units of this. The units have to be newtons per meter cubed, right? They can't be. So what should actually I be putting in? So clearly the body force is written in terms of this expression. The body force is a body force, so it's Newton per force per volume, which is the classic way of defining a body force. Here, the units of the body force that would go into this are stress per length, which is so these body forces by definition are this is a body force. So Bx is equal to what we're calling Fx. And so you're right. So the magnitudes of the displacements, once we put them in here, this equation, which would be this equation at the bottom, would not be, it would be not a function of time, right? So yeah. So this body force should be without this term. So you're exactly right. So the body force for the units to work should not have this term. Body force has to be equal plus or minus alpha times dp dx. And of course, pressure is in newtons per meter squared. 1 over length is meters. And so it's exactly the right units for that. Yeah, okay, great. Now I got you. You're exactly correct. And so what we would do is just this, right? So what's the change magnitude going to be? Okay? Is that what you meant? Or are you still worried just the fact that it's red? The reason it's red...
it's because you use the diffusion physics.
Yeah.
You
it doesn't...
replace P with C,
right.
That's
yeah,
why.
yeah.
But if you get rid of the T term, that would be correct.
Great, so that's right. And so these are the individual components. So that's the coupling. So those are the two components that we have. We're rapidly running out of time, so we don't. I didn't put in boundary conditions, but I will go back to this other, the diffusion equation, just to make one other point, because it's written out here. And that is that this term here on the right-hand side, this r, which we've added, which I think we have it in kind of the right way, is this term. It's getting really messed up, and I can't overemphasize it anymore, but it's this term down the bottom is this r term. The other term which is in here is the portion that we've just accommodated with this 1 over q. And so the appropriate magnitudes that we use for this are this. So, yeah, okay. So, do you want to give it a go? You've got 3 minutes, 2 minutes, think you can do it? So what the bound, where are we? We're in diffusion. So the boundary conditions are pressure and concentration, which is 0. Great. We'll race against time here. Physics, boundary settings. Let's, for our geometry that we have, well, we have Poisson ratio of 0, so it doesn't matter. So we can put 0 displacement on all these boundaries. Which is constraint is can't do that. So displacement in x is 0. Displacement in y is 0. Load on the top. I'm not going to that class today. What is y? It's a force. And so it's -1, I think, right? Given the right geometry, pointing downwards. Positive y direction is up. Do you think do we have enough there for it to run? Well, give it a shot. Doesn't like it. So what doesn't like it? It doesn't quite like this. Don't know why. Well, I'm going to save it and I'll mess around with it. I think I'll be able to get it working. File, save as. Okay. Maybe I'll send that to you and let you figure it out. Or perhaps I'll figure it out. So that's the idea. So maybe not as smooth as we hoped. It'd be nice if BO had opened because all that stuff is in there and working, and we could have used the validation stuff. But you have some information on how to calculate from the constitutive behavior, fluid pressures, stresses at certain stages, and the rates at which they might asymptote to those. You have some knowledge now of what the coupling should be, these off-diagonal terms that allow you to link it. And that's kind of the essence of what we're kind of doing in terms of linkages. We didn't talk about thermoelasticity, but thermoelasticity is actually directly analogous to poroelasticity. The body force in thermoelasticity is the thermal coefficient of expansion multiplied by the thermal gradient, dt dx. And it's exactly analogous. It's a one-way coupling. You apply a temperature, you get a deformation. You can't apply a deformation and get a temperature in the same way as you can in pore mechanics. You apply a deformation, you generate undrained fluid pressures, which then respond. So they're very similar, they're analogous, but the coupling is really only one way. Okay? So I will send you the BO file, and so with some things to do. Just you might enjoy trying to work out exactly how it works. Okay? Great. Thank you.